Good evening, everyone. Welcome to Fire Ecology of Oregon Forests, another webinar in our many series that we've offered over the past few years. I'm John Punches. I'm the Extension Forester in Northeastern Oregon and an Associate Professor at Oregon State University. Happy to have you with us. We are embarking upon a series of webinars over the next 3 months that are going to dive into some pretty cool stuff around fire-related ecology, both in Oregon forest, but also adjacent and intermixed ecosystems. So trying to be a little bit inclusive in that. And we've got some great speakers lined up over the next 3 months. I'm really excited about this series. My job tonight is to kind of set a foundation. I'll provide some kind of basic terminology and get us thinking about how this process works and kind of some of the foundational information that helps us be able to interpret the ecology of our forests and other ecosystems. So not trying to be all inclusive and certainly not claiming to have all the answers or all the information. Just like in the hour and a half that we have together, we won't even be able to really skim the surface. And so we'll use this to build a foundation. Just a little bit of detail around how this works. So webinars by their design here, I'm going to be presenting to you tonight. I've got a group of folks who are available to help answer questions. So we would really appreciate it if when you have questions as a participant, please use the Zoom question and answer feature to do that. So enter your question, and then if it's a kind of a general question that one of the other folks can answer, they'll do that. Otherwise, one of them will direct them to me when I stop periodically to answer questions. Jake, are you available to talk to folks a little bit about how they can get continuing education credit?
Yeah. Good evening, everyone. My name is Jacob Putney. I'm the Extension Forester in Baker and Grant counties. And so continuing education credits are available for both the Society of American Foresters as well as the Associated Oregon Loggers. If you're interested in SAF credits, there is a form on the series website. If you download that form, fill out your name, CFP number, email, and then there's going to be a keyword that I will announce at the end of this session tonight, as well as all of the sessions in the series. And you fill out that form and return it to me, and I'll get those credits recorded. And for SAF credits, you can either fill out one form for each webinar, or you can fill them out and then return one form to me at the end of the series. And then for Associated Oregon Loggers, Oregon Professional Logger credits, if you just shoot me an email with your name and email and company that you're representing, and I will get those recorded as well.
Thank you, Jake. Now, I'm periodically getting a little note here that says my internet connection is unstable. So Jake or one of the other folks, if you're starting to hear or see that things aren't working quite right, holler at me. I could turn off my video, but keep the screen going. That might free up a little bit of bandwidth. So just let me know if that becomes an issue. So with that, I'm going to dive into this and just ask, again, use the Q&A feature. If you've got kind of side comments, feel free to use the chat, but please keep it clean and nice. All right, with that, let me just jump right into this. So as I mentioned, we're really pleased to bring this series to you on fire ecology of Oregon forests. We all work in this kind of realm as we think about forestry, as we think about forest management. I know that every time I talk to a landowner about how they manage dry forests in northeastern Oregon or really anywhere east of the Cascades, I always find myself talking about fire and its long-term impact and interaction with the forested ecosystems. It really is the driver that's helped these ecosystems evolve and is a really important thing for us to understand as we're trying to think about how we steward those forests into the future. So as I mentioned, my job tonight is to kind of build a little bit of a foundation. We call this first in the series, the principles of fire ecology. And I'm really just like going to skim the surface. There's no way that we can dig deep into this in the amount of time that we have. Next week, one of our colleagues, Micah Schmidt, is going to talk to us about fire regimes and be able to hone in a little bit more. He's done a lot of really essential work in that area. Then after that, in our third session, we'll think about the impact of fire on soils. Ari Cowan is going to be with us to talk about that. And then we have some just great speakers lined up to work through a series of different forested and non-forested ecosystems, really kind of dig in and give us a sense of how those plant communities are interacting. So I'm super excited about what's coming up here as we go through this series. Just a reminder that as we do with all of our webinar series, we maintain a website specific to this series. This one's called Fire Ecology of Oregon Forests. There's a link to it in the reminders that you've been getting from Zoom. That's where, if you want to come back and listen to a recording of this, we're recording it now, and I'll post that as soon as it becomes available, probably tomorrow. And then we also post a variety of additional resources there. So I've got a paper that I really think is a kind of an essential one, something that helps overview. It also is called Principles of Fire Ecology. That was kind of happenstance. And then some other resources. There's a series that was called the Rainbow Series that we're looking at fire effects on different resources. And those are a really good series of U.S. Forest Service publications. So I posted those there as well. And so you'll find some good resources there, along with links to previous webinar series that we've held. And as we go through this series and each presenter provides their materials, many of them will also provide additional materials, but that'll always be the place where you can go to find the recordings. All right, I'm going to jump right in. So let's take a minute and just define fire ecology. Actually, not an easy thing to do. So if we just define ecology, that's the study of relationships among organisms and their physical surroundings. So that's very inclusive, right? And it needs to be, because ecology is that sense of understanding how things mesh together, right? So when we add fire to that, you can kind of note here that there's a variety of different definitions if we go through the literature. So one is that fire ecology is the study of the effects of fire on natural ecosystem. Makes sense to me, right? Or it can be the study of fire and fire regimes in ecosystems. Those fire regimes are certainly terms and concepts that we utilize in thinking about the ecology of these fire adapted systems. So how about fire as an ecosystem process? Okay, that makes sense to me. It is a process and it incorporates with ecosystems. Here's a little bit bigger one: ecological patterns emerging from interaction of fire processes and ecological processes. Wow. But think through that. Yes, it's those patterns that emerge from the interactions of fire and its processes with everything that's happening in that ecosystem. So that's a good one. I like that one. But I'm going to go even farther, and this is one that I have borrowed from a colleague, Dr. Meg Krawchuk. She says that we need to think about fire ecology as the study of natural and human fire history and fire effects on the environment, species, ecosystems, and landscapes. So really inclusive. And I think, to me, what is really important in that particular definition is that it includes humans in the mix. We humans have been integral with the propagation of fire across Earth's landscapes for as long as we've been humans. And so I think we really need to recognize that and have that be part of our overall definition. So there's just some really kind of foundational options for how you would want to define this, and you can kind of pick and choose whichever one you think is most important. But we'll start with that as just kind of laying that foundation, and we'll kind of build some pieces here over the next few minutes to kind of bring that all together. So now I want to just step back and I want to have us think about fire. So fire, I think, is best described as a biochemical process. So it's a chemical reaction, but the way fire operates in an ecosystem is that it's utilizing biomass. So it's the biomass is the fuel source for this chemical process. So combustion takes carbohydrates in those plants, that fuel material, it oxidizes them. In the process, it releases carbon dioxide and water, and then energy. So it takes some energy in to get it started, but once it starts, then it's releasing carbon dioxide and water and energy. Now, if you think about that, that is the opposite of the process of photosynthesis. Photosynthesis uses energy from the sun in order to grab carbon dioxide out of the air, and it combines these materials to create those carbohydrates, which then get remade into all kinds of different plant products, right? So fires are essentially reversing the photosynthetic process, and that's nature's process of recycling. So photosynthesis creates, and then fire recreates it back into a different form and allows that process to continue. I think those are really important concepts to kind of have in, as part of this foundation, right? So if we think about how fire occurs, in order for fire to occur, you got to have three things. You got to have fuel, you got to have enough heat to cause ignition, and you got to have oxygen, and then you can have combustion. And if we were to map these out across some axes that look at a spatial scale and a temporal scale, so space and time, combustion occurs really instantaneously and really localized. So at each individual location and time, you're going to have a certain amount of combustion if you have those necessary precursors, right? And if we take any one of those away, if I take the fuel away, if I take the heat away, if I take the oxygen away, then combustion stops at that location. Maybe not next door, but it happens at that location, right? And so combustion is one of these fire triangles that the fire folks often talk about. And this is really the way that we think about managing fire, is to remove the fuel or remove the heat or remove the oxygen, one of those three options there. Now, when fire operates in nature, in an ecosystem, it doesn't behave uniformly. It's going to have different effects in different areas. And those complexities are really important. So if we look at these two pictures here, you can see a kind of a landscape scale burn in here. We've got some patches that are quite burned. You might call those torched. You've got some patches that are kind of brown. You might call those scorched. You got some patches that are still green, so unburned, or maybe those are going to be what we call refugia. So those are the places where the seed sources remain, where the animals remain or can flee to, where there's the biotic components to repopulate soil biomes that may have been heated up and lost some of their components. And so these are really important. This variation in fire intensity and severity across the landscape are really important. But if we dig in deeper, if we were to look deeper into these areas, we'd find out there's a huge amount of variation, even at a very localized scale. So here we can see that there's been fire that's burned here, but not right here. And so it's always that case that we find this wide range of severity across the landscape. But then even at very fine scale, we still find that range of severities. Now, I'm using a term that maybe you're not quite sure how it's utilized in fire sciences and in fire ecology. So let's take a minute and define a couple of important concepts here. When fire ecologists or firefighters, fire scientists describe fire, we commonly use two terms: intensity and severity, and they don't mean the same thing. Now, lots of people use them interchangeably, but they really don't mean the same thing. So if we just kind of dig in a little bit deeper, the easy way to think about these is that fire intensity is talking about the amount of energy the fire is releasing. So think of it as heat. How hot is this fire? So here's an example of a low intensity fire. You can see that the flames are pretty short. So we would say that has a low flame length or a small flame length. Here we have a crown fire, and there's significant flame lengths in here, and even combustion extending up into the atmosphere. So huge amount of heat being released from this particular fire. So this is a high intensity fire, whereas this is a low intensity fire. Now, that's all well and good, but just because we have a low intensity fire doesn't always mean that we have limited impacts on what's under or around that fire. So let's dig a little bit deeper and add that other term. So when we think about severity in the ecological context here, in this fire ecological context, is the degree of change resulting from the fire. So here I have demonstrated a low severity fire. So the fire burned through, and we're looking at that probably the spring after the burn. We can see that the grasses have returned, some of the shrubs have returned. The trees themselves didn't really get impacted. There's a little bit of char on the lower parts of the stems. Maybe they got a little bit of scorching up here in some of the lower branches, but the upper stuff is fine. So really, like, that ecosystem is intact. It didn't really change much. Whereas this example, the fire burned through here, it was hot enough to kill these trees. It removed their foliage. In the process now, there's a lot more light getting down here to the ground. The snow over the winter would get to the ground here instead of being captured in the crowns of these trees. So there's going to be a little bit more snow remaining in this site. The ground cover now is likely changed relatively significantly. There's going to be a lot more vegetation here at the surface level in this understory because now it's getting light and it has more moisture available to it from that purpose, right? So this would be a high severity burn because there's significant change. Now, the challenge with talking about severity is that severity can be different depending on what you're looking at. And so if I talk about my above ground severity, the severity to the vegetation, we look in here, we got lots of burned trees left over in here, right? So that's severe. Here we've got lots of burned trees. So to the vegetation above ground, high severity. But that doesn't always articulate to high severity at the soil level, right? So in this particular photo, I would argue that we've got high severity here around where these shrubs were because they had more biomass that built up and so they could support fire for longer and at higher intensity. It could transmit more heat into the ground, into the soil. And so we've got high severity there. But these adjacent areas that didn't have much vegetation are probably relatively unimpacted. They may have even a low severity. Maybe it just kind of flashed off some grasses here and there, and it didn't really change much of the condition of those areas. So we've got a matrix, if you will, of severity within this particular burn, whereas this one, boy, that's looking high severity every place, right? So my point here is that high severity to vegetation may not result in high severity to soil. It might, but it might not. And that reverse there is that high severity to soil might not be high severity vegetation, although typically if you've got high severity to soil, you've probably also got high severity to adjacent vegetation, but you might not see it right away. So an example of that would be a smoldering combustion in deep duff that maybe you don't really even see any real impacts on the adjacent vegetation until maybe several months or a year later when you found out that there was enough heat there to kill the root systems. And it took time for that to actually appear. So maybe there's going to be a delay between when we see that. But the point here is that intensity and severity are not the same thing. So put that in your tool bag, if you will, that intensity is the term that we're using to talk about the heat of the fire, the amount of energy released from it. And severity is the resulting impact on that ecosystem. And we got to get a little specific to say, what are we actually talking about, right? When I do this with my students, we even get like even deeper into this because there's all kinds of different strata within any particular ecosystem where we can have different levels of severity depending on how that fire carries out, right? So that suggests that if we've got differences depending on where you are across the landscape, that maybe we need to have another triangle in here to think about how fire would actually impact any particular location. And we call that the fire behavior triangle. And within that one, we change it up a little bit. We've still got fuel as the kind of foundation for how fire is going to react in any particular location. But the actual impacts of the fire, its behavior, is going to be really heavily influenced by the topography. So if I have a steep slope, it's going to burn hotter and faster going upslope. If I have a narrow canyon, it's going to, maybe the wind's going to funnel it up that canyon, or it might form a chimney-like effect up that. If I have a saddle, that almost always becomes a hotter spot in the burn. And then all of this is going to be impacted by weather. If I have a cool, moist day, not going to have much fire activity, even if we manage to get one started. Whereas if I have a hot, dry, windy day after a long dry spell, that's going to be the fire that can really rip. And then that's going to, what's actually going to happen there is going to depend on that intersection of fuel and weather and topography. So we got to put all of those pieces together. Right. So when the fire burns then, the observations that we as humans can make kind of fall into two categories. There's some things that we can see right away. These are the direct effects of the fire. So if you look in this photo, The direct effects would be the combustion of some of the woody material here that was on the ground. It's the combustion of the above ground biomass that was in the grass and in the shrubs, right? It's the charring of the stems here, the bark on the trees. It's the scorching of some of the foliage on these trees here. So that happens relatively soon after the fire, and we can see it, we can observe it. So think of those as the direct effects. But a lot of the effects of fire don't come directly. They come as a secondary effect. So maybe the fire causes the scorching of these needles in here that stresses the tree, and then later on bark beetles come in and cause additional damage, and that might not actually appear for a year or 2 years or sometimes even 3 years, right? Or it might be that we have enough heat buildup in the soil that we damage root systems, and again, that produces stress that later on has impacts on those trees or other plants. So we call those second order fire effects. So first order fire effects are the direct effects, and second order fire effects are the indirect effects that come in response to the first order effects. So some more terminology. So you got fire intensity and fire severity. And now we're thinking of how we observe the results of the severity and the intensity in the combination here of first order fire effects and second order fire effects. So this is kind of the combined way that we think about the impacts on the landscape, and this is then going to in turn become the way that we see the ecology adapt to these impacts. Now, as I mentioned before, fire has a lot of variation in the way that it responds across any particular landscape. And so if we look in this picture, this is in the strawberry wilderness, and we can see areas in here that burned pretty intensely and probably would be, from a vegetation perspective, had a pretty high severity level. We can see areas that were missed completely. There's no fire in this whatsoever, at least that we can observe. There might be a little bit at the surface level that we can see. And there's areas in here that was kind of mixed, and so the fire crept underneath these, didn't torch out all the trees, but killed some. And you can see a real kind of mosaic pattern across the landscape here, where lots of trees got killed, but there's also lots of still green in here. So that's going to be the reservoir of seed that's going to repopulate these more open areas. But we're also going to see lots of change in this in the vegetative community, because that fire has opened up and made a different set of conditions here receptive to different plants and animal species. And so that idea or that realization that fire isn't binary, it's very nuanced. It forms typically a mosaic pattern across the landscape, and this is really important for the effective functioning of our ecosystems. All right, so with that, maybe I'll pause there and just ask if there's any questions that have come up. Do we have anything in the Q&A box so far? Not seeing any questions in Q&A. But there might be one chat. Okay, series website. Okay, so I think we're good. All right, then I'm just going to move on, and remember, use that Q&A if you have questions. So we've got a little bit of a foundation set here. So we've got some terminology. We've got this idea that fires need certain things in order to be able to actually occur. There's a combustion level that's very like fine scale and very instantaneous, and then there's this fire behavior triangle that we've been talking about that's kind of that little bit bigger scale, and we're looking at that intersection between the fire and the weather and the topography, right? And you can see the variation across this landscape that resulted in, right? And so we're going to see first order fire effects, and we're going to see second order fire effects. Now, that's all well and good, but fire doesn't occur just once and then never again, right? So fire occurs, and then nature rebuilds this community of plants, and it replenishes that fuel, or maybe even it burns once through here, and now there's all this dead material that eventually falls over and becomes fodder, if you will, for the next fire, which would then burn differently because the fuel available to it is different in size and shape and loading and things of that nature. So we need to think about fire as being something that recurs. And it's not just something that happens occasionally. If we look across our planet, fire is present and has been present in every terrestrial ecosystem. Now, maybe somebody could argue that there's some terrestrial ecosystems that don't have it. So maybe we could go to Antarctica or maybe like the northern part of Greenland, right? Um, but every place that has the potential for combustion, if it produces fuel, if it eventually has a dry spell, if it eventually lines up with an ignition source, we're going to have fire there, right? And so terrestrial ecosystems are just kind of dialed into having fire. But that doesn't mean that they have fire all the time or that they all have it on the same scale and basis, but we have lots of fire on our planet. This is a fire planet. And so this is a cool kind of satellite assemblage that comes from NASA. And this is from July of this past year. And all the red areas are places that had fire in the month of July across our planet, just this past year, right? So you can look at these across history and past year, like we had some outliers, but for the most part, it's pretty on track there. You can kind of see that there's a band of fire in kind of these kind of mid northern latitudes. And there's also kind of a band of fire in the mid southern latitudes. So even though like July is summer here and July is winter here, what really drives the fire patterns is when do they get their moisture. And so for the southern hemisphere, it's like when do the monsoons hit through here? And by hitting July, it's kind of hitting in here right before they're going to start to get the rain. So this is also part of their dry season. So dry season fires. Now we can go one more and go to January, and you can see that we also had fires in January. And so California is burning, parts of Oregon are burning, parts of Mexico and South America are burning, right? But they're slightly different. Here's a band right here in Africa that was a little bit different than what we saw before, and a band that kind of shoots up here through India and so on. And if we back up and kind of just like let this mirror in your eyes, right? So there's July, and then there's January. Let's see that one more time. There's July, and then there's January. So can you kind of see the pattern of how fire can change its locations over time? But there's some areas here that are pretty conspicuously devoid of fire. So I'm going to open up and just ask you to respond in the chat box. I didn't do a poll for this, but go ahead and give me a little participation and jump into the chat box, not the Q&A, just chat box. Where in the world are the places where you don't see any or much fire? Where are you not seeing fire based on these maps? So just drop that into the chat box and I'll pull it up here and we'll see what people are saying. Okay. So I'm seeing Sahara, Russia, deserts, places that are low in vegetation, Morocco, yep, the poles, exactly, yep. Far north, yep, Greenland, yep, Northern taiga, yep. Awesome. Yeah, yep. Lots of comments on deserts, right? Tibet, yep. So if we were to summarize that, right? So if we look across these two, I'll back it up here again. So there's the summer burns, right? So in our region, summer burns are pretty common in our southern and our southeastern and our western states, right? And we get pockets of burns. And in 2024, we had some pretty big burns high up into kind of the more northern regions of Canada. So big fire year in Canada, right? And it's not always that way, but these far north regions, a lot of black spruce in there, and it's a fire adapted species, but it doesn't burn all the time. But when it burns, it really burns, right? And so we've got some areas that are really burning up in here. But we can also see this combination across, the same kind of configuration across Europe and across here through Russia and so on. We've got kind of a band through here, through South America, and through the kind of the southern part, if you will, of Africa. And so these are areas, again, that this is the dry part of their season, and these are, but also places where there's enough moisture that they actually have enough vegetation to carry out fire. And then, like both times a year, the places where we don't see fire typically are these areas that are just so dry they don't have enough vegetation typically to support fire. That doesn't mean they won't ever support fire, because if they have a few years or a year when they get more rain than is normal and they get lots of vegetation, then once it dries out, then it's susceptible to fire because they've got otherwise the conditions amenable to fire. So we have a fire adapted planet, and we've had it that way for a really long time. So if you kind of look through the geologic record and go back in time, there's evidence of fires in the geologic record as far back as 440 million years before current. And so that's a long ways back, right? And that's, we're actually finding charcoal that old in various contexts, right? So that means that in order for that to happen, things had to happen on our planet to make it possible. So one, there had to be enough action of organisms that could produce and release oxygen. We had to have enough oxygen in the atmosphere to support combustion. And then we had to have terrestrial organisms that could grow, produce biomass, die and dry out, and become like susceptible or receptive to fire, right? And so that's like that 440 million years ago is pretty commonly accepted as like that's the farthest back in the geologic record of where we think we have that combination of terrestrial plants and then enough oxygen in the atmosphere to be able to carry out fire. And then fires occur and they recur and they have these combined impacts on the ecosystems. So from that point forward, our ecosystems are being formed and informed by fire. And so that leads us into thinking here about that like next triangle we might look at in our space-time scale here, that would be fire regimes, which look at not just fuel, but what's the mosaic of vegetation within any particular area. What are the ignitions? When do they come? How frequently do they come? So when do we have those potential for ignitions? And what's the overall climate? So that longer term weather, because that's going to define, like it's all interaction there for defining how the vegetation is going to grow, what vegetation is going to grow, whether or not it will ignite, how frequently it will ignite, and then whether we have receptive fuels. And so fire regimes are that intersection of those three characteristics. So we've got our three kind of primary fire triangles now with combustion, very instantaneous at a really fine scale, the fire behavior, intermediate scale, and intermediate time frame, and then longer time frame and much bigger spatial scale for the fire regimes, right? So in the United States, we are actually really fortunate to have excellent scientific evidence, scientific study recreating our historical fire regimes. So we kind of know what the landscape was relative to fire because we've got just a wealth of studies that have been done on that, more so than really any place else in the world. So we've got lots of information, and this is kind of a cool map out of the land fire program that takes a stab at kind of pictorializing what these fire regimes were. And so if we look here across the kind of the central part of the United States, you can see these are pretty brown in nature here, in color here. And so these say that the mean fire return interval, how frequently did fire return? So these really dark brown areas, every 1 to 5 years. These little bit less brown areas, every 6 to 10, and so on. So a lot of this area in here is burning every year or maybe every 20 years, right? So in that time range in there. So again, let's jump into the chat box. What is the like unifying characteristic of this central part of the United States that would allow it to have such frequent fire activity? So what's going on there? So I'm seeing lots of grass and grasslands and plains. Yep, exactly. So that's exactly what's going on there, right? And yep, intense storms. So we get thunderstorms across that. So there's something there to serve as that ignition source. Exactly, right? And it's really interesting to think about if you dig into it. There's a very strong interaction between the vegetation here, the frequent fire regime, the sources of ignitions within this, and also the animals that populated those plains. So there were large ungulates, lots of bison, but others as well. And they were things that also modified that fire regime. They consumed vegetation and kept it short in places, but they also, when that vegetation became a little aged, then it would grow up and they weren't there as much, and that's where the fires would go through, and then those animals would come back in and follow through after that. And so very kind of interesting interaction between the plant community, the animal community, and this whole fire regime concept. Now we're over here in Oregon, and you can see that there's a portion of Oregon, Southwest Oregon, with pretty frequent fires. There's a portion that's East Side Oregon, again with pretty frequent fires, and some of this just shows like where was there burnable material. And then there's some areas here that are, our Cascade Range and our Coast Range, and those had the longer fire return intervals. Now, I'm not going to dig a bunch into fire regimes because Mike is going to talk a lot about that in a couple weeks. So I don't want to steal his thunder there. But I will say that we have to be careful about thinking of a fire regime as dictating like the minimum fire return interval. So these areas in here in the Cascades and up into Washington show really long mean fire return intervals. But that doesn't mean that there weren't more frequent low intensity, low severity fires that kind of crept around in small locations. What it's really saying is that the thing that defined fire across the larger landscape was these less frequent, higher intensity fires. Whereas if you get into East Side Oregon, these are more defined by more frequent, lower severity fires, right? But that doesn't mean that there aren't occasionally high intensity, big fires. It happens, right? You just get that combination of conditions that allow that to occur. So we want to kind of keep that in our mind that when we're thinking about fire regimes, it's not a dictation of an exact condition, but rather a representation of what commonly occurs and then a recognition that there's a lot of variation within that. All right, so let's build on this a little bit and just recognize that from an ecological perspective, every time there's a fire, that fire is burning in a way that responds to what happened in that ecosystem in the past. That's what helped define its fuel conditions, the vegetation conditions. That may well mean that the previous fire is now setting up the conditions for this current fire. So it may have less fuel, it may have more fuel, it may just be different fuel, right? That said, the what happens currently is going to depend on the current conditions that ecosystem experiences. And then once it burns, that sets up the conditions for the future ecological advancement and adaptation, but it's also setting up for the next fire. And so these things they're never a one and done. It's always on a continuum and they're very much cyclical, right? So if you think about this happening time and time again in any particular environment, it means that plants have had a really long time to be able to change in response to the pressures that they experience from that fire. So I don't know how well you can dig in and see this, but this is a cool area where I hike up and down a mountainside. There's no trail or anything, but I've just hiked up and down it dozens and dozens of times over the years because it's kind of my exercise spot. Super steep, right? And for many years, it was just a really dense understory, and it really had very little there. Like there was very little plant mass growing in most of these places. Just leaf litter and branches falling off the Douglas fir trees. And then fire burned through it, and it really opened it up. It killed a lot of the trees, and I was super surprised to go through there one early spring and just find dozens, not dozens, hundreds and hundreds and hundreds of Mariposa lilies that I had never seen there before. Didn't even know they existed there. And they are fire adapted to the extent that when a landscape is opened up by fire, you tend to have a real intense blossom and flowering effect from the Mariposa lilies. And so these plants didn't just show up there and seed in, they're perennials. They had been there in their bulb stage, dormant, probably for at least 60 or 70 years while this was a super dense stand of Douglas fir. And then once it's opened up, bam, there they are. So that's an amazing adaptation to fire that allows this plant to have long dormancy periods and then really active flowering and hence fruiting once it has the right conditions. So this is a plant that like has a certain resiliency to fire that's built into its life cycle. And there's lots of examples of that. So if we kind of think and try to put some categories around how plants respond to fire, I think you can kind of put plants into these three categories. Now, there's lots of other ways that ecologists kind of dig in and describe this stuff, but these are pretty common, right? So one way that plants can be like adapted to fire is to be resistant to them, to have some way that they have some traits, some physiological or morphological traits that help them lower the probability of being killed or injured. So here's a classic example, ponderosa pine. So thick bark, particularly in these bigger, older trees, right? It's also bark that it's flaky, and when fire gets on it, the flakes actually kind of curl and then they fall off. And I've done a lot of burning in ponderosa pine, and you can just watch fire kind of creep up the stem and then fall off. It literally falls off, and that protects the tree from having lingering fire where it could cause damage, right? You'll also notice that the branches, like the base of the living crown, is relatively high on these trees. That's partly from having fire underneath scorched it in the past, but these trees are so intolerant of shade that they will shade out their own lower branches. And that gives them some protection from the flames down here because it just means that their green foliage is farther away from it. And notice that the foliage is way out at the end of the branches. So if fire does happen to creep up the stem, it has a hard time reaching the foliage. So that's a resistance adaptation, right? So another way that plants can be adapted to fire is to be sensitive to fire. So easily killed or injured. So here's lodgepole pine, kind of the other end of the spectrum. You know, fire comes through there, pretty thin barked, and they're just really receptive to ground fire. And so really commonly when fire comes through a stand of lodgepole pine, all the lodgepole pine get killed, or at least most of them, right? So that's a fire sensitivity that kills off those more mature trees. But overall, both of these species have a resilience to fire. This one does it by surviving the fire. This one does it by having its more mature individuals killed. But if they're cone bearing, remember that the lodgepole pine, at least a portion of their cones are serotinous, meaning that they stay closed up and then they're heat activated. We'll talk a little bit more about that in a minute, but they're heat activated, and that then allows those cones to open up and drop their seeds. And there's a little bit of a delay mechanism in there, so they're not dropping them into hot ash or existing fire. It gives a little bit of time so things can cool off a little bit. And now they've got this nice, really open, seed bed, and out come the new little seeds, and we get lots of lodgepole pine back. So lodgepole pine is also adapted to fire. Not that the individual trees survive a fire typically, but that their population survives by having abundant natural regeneration following the fire. I'm going to stop there and see if we have any Q&A. So William says, fires in Australia usually make the news. Why don't we hear of fires in Southern Africa or South America? Is that just because of fewer impacts to people? I think it's in it. I think Bill. I think the answer to that is that if you lived in those places, you would hear about that. I think we're insulated from that simply because we don't have as much of the information about those areas. If you get far South Africa, some of those areas have longer fire return intervals. Same for far South America. That's the equivalent of our northern latitudes. And so that can be part of it too, that they're probably less frequent in some of those areas. But there's a lot of fire there. And so I think that in a lot of cases, we're just simply not hearing of that. We just don't have the news feed from those parts of the world, right? And then Donald asks, why does the well-forested East Coast have short return intervals and presumably low intensity fires? So historically, and we're going to have, is that right? So I was going to say we have a webinar on that, but we don't. Sorry, I'm thinking of the wrong class. I'm teaching two of these simultaneously. Um, but historically, a lot of those forests burned relatively frequently because there's a lot of leaf litter that accumulates from those hardwoods, and they often burned in the winter months, is my understanding. So I'm not an expert over there, but I think historically they did have a lot of that. And now they're experiencing some of the same issues that we're seeing in our western forests with long-term fire suppression, allowing those forests to actually change in their composition and structure. And so they're having different fires there as well. Um, Nick, hey Nick, have there been studies on the effects of exclusion of post-fire disturbances, much like the lack of grazing animals in the post-fire landscape, as restoration tends to focus on recreating and sustaining pre-fire conditions? Let me ponder that a minute. Have there been studies on the effects? So yes, there have been studies. I'm not an expert in those studies. So that's a good one. Let's do some follow-up work on that, and I will see if I can find a good paper or two to add to the website to think about the impacts of grazing on post-fire landscapes. There's plenty of work looking at that around grazing of livestock, but I think you're maybe asking more around like native ungulates, wild ungulates, and stuff like that. So maybe shoot me an email, Nick, and ask me more specifically what you're doing there. I'll see if I can come up with some better information on that. Michael asks, is the capacity of resilience proportionate to the prevalence of historical fire? So a process of evolution. So super question. And what I would say is that in my mind, all ecosystems have some form of resilience to fire. So maybe that means that they exist in ways where, like ponderosa pine, they're really tied and well suited to a short return interval, so frequent fire at low intensity. Um, Maybe it means that they're like black spruce, tied to a little bit longer fire return interval, and a higher intensity, but then a better capacity for regeneration following that. So lodgepole pine would fall into that as well. Or it could be that you're a bog plant that has relatively infrequent fire, and you're adapted in such a way that you live in a bed of sphagnum moss that holds moisture, will even hold it above like the water table gradient, and so you're less likely to have fire because of that positioning that you have. So there's lots of different ways that plants can be adapted to fire. Doesn't necessarily mean that they're adapted to having fire, um, but there's different evolutionary pathways to help them survive in the midst of fire. And so, yes, this is all tied into that process of having traits that allow you to um, exist in places under certain fire regimes. And when we're out of sync with those fire regimes, then it's harder for those plants to continue in that ecological system. Okay, so lots of other ones here. I'm going to kind of come back to some of these because we're going to talk a little bit more in a minute about some of the impacts of humans in these systems. So I want to come back to that. So excellent questions there. I'm going to X out of that and continue with a few more slides here while we still got some time. All right. So I want to spend just a few minutes thinking about different ways that plants can be adapted to fire. So this isn't all inclusive, but I think this will hit some of the major ones. So one way that a plant can be adapted is to be resistant through having bark that protects them from the effects of the fire. So I gave the example of ponderosa pine, but Douglas fir is another one of them. Both are west side Douglas fir, the coast Doug fir, and our interior Rocky Mountain Doug fir, same species, but different varieties. They're both very well adapted to fire from the point that they have bark that helps insulate them from fire. So we've got the really thick and corky bark of Douglas fir. So once they get to a relatively large size, these characters are pretty dang resistant to fire, right? Now that doesn't mean that they're going to survive if there's a lot of fuel load on the ground that's going to result in high soil severity of fire that might damage those trees' roots and kill them that way. but just having some fire around them and having fire adjacent to their stems, they're very resistant to that. Oregon oak can be another one of those. In the larger trees, the oaks are going to be pretty resilient to fire, pretty resistant to fire because they've got that bark depth that helps insulate them. So here's a cool little figure that looks at bark thickness for different species, but also says, let's think about what that bark thickness is actually buying. It's allowing tree species, to be resilient or resistant to a period of heating. Okay, so this axis here is giving like the amount of time in minutes before the cambium gets too hot and the resulting tree is killed in that area here. And you can see that there's a bunch of different species listed here, and these resistances increase with diameter. Okay, so bigger tree, thicker bark, longer time frame before the thing dies, right? So Doug fir, really resistant based on bark thickness, right? So the really corky bark. Western larch, very similar. Okay. Ponderosa pine, a little bit different bark configuration, but again, very resistant. So these are our big three. But again, if they're little, so 10 centimeters, about 4 inches. So if they're little, it doesn't take very long to heat them to the point where you're going to get some cambial death, right? By the time you get out here to 60 inches, that's about 60 centimeters, about 24 inches. You can see that there's a significant amount of time that these bigger trees can endure that heat being there adjacent to their stem before they're going to have that cambial death, right? But if you get some of these other species, like get down here with Engelmann spruce, western white pine, western red cedar, lodgepole pine, subalpine fir, they just never really build up the bark thickness and the bark characteristics that allow them to be resistant to the longer term heating from fire being adjacent to their stems. Grand fir and western hemlock are kind of intermediate in this, but they've got to build up to a pretty good diameter before they have a whole lot of resistance there based on their bark thickness. So different characteristics based on not just the thickness of the bark, but also the construction, if you will, of the bark. The amount of cork, is it spongy versus shreddy, things of that nature. So key feature, but very much different across the landscape based on the species. Okay, so another way that plants can have some ability to interact with fire and survive that is to have different ways that they recover after fire. So I'll just pop these up here so we can talk about epicormic sprouting. So there can be protected buds embedded in the bark of some tree species. Fire might come through and burn off their existing foliage, but those protected buds, then if that hasn't been too much heat in there, those buds can break and they can repopulate the stems of those trees. So we find that in some of our oak species here in the Pacific Northwest. We find it to some extent in Douglas fir, to some extent in our AB species. If they survive, they might have this potential to have some epichromic branching that can help them recover from that. A lot of our shrub species and some of our tree species are going to have this ability to have like all of their above ground woody biomass kind of burned off, or at least a substantial portion of it, and then they'll get sprouting back from either the stump itself or the root crown right around the edge of that, and that repopulates. So many of our shrub species do that. So some of the ceanothus species, if you get down into like the Northern California area there, where they have the chaparral kind of stuff, the chamis, they really are kind of well known for this. For us, like our species that are in the like bearberry, or excuse me, and some of our manzanita species can do this from time to time if they don't get too hot. They've got that ability. A lot of our rose species will do that, and so a lot of capacity to have this follow-up reaction to the fire that allows that shrubby species to regenerate pretty fast, right? I find that in maple a lot. So we'll have burn over, the maple tree dies above ground, but the root system stays alive, and we get a lot of regeneration in maples, right? And then with some of our species, a few species like trembling aspen, quaking aspen, those like they really regenerate best when they have a fire that goes through and kills off all of the large stems, all of the mature stems that were there, right? Because that changes the chemical system down into their roots and they get suckering from those lateral roots. And so they get, development there of stem tissue, and all of a sudden you've got a whole new copse of quaking aspen that replaces what was there before. And what's interesting in those is if you don't get really complete killing off of those existing stems, you don't get anywhere near as much sprouting activity. So you got to have pretty, high severity burn in that above ground in order to have the really robust sprouting action. So again, that's a adaptation that plants can have in order to be able to respond to fire and maintain their resiliency over the long term. So another way, and we talked about this with the example of lodgepole pine, is that plants can have seeds that have like a timing mechanism or some cue that they need to receive in order to know that like it's time for them to open and drop their seed and so they can regenerate effectively. And so serotinous cones just mean that they're closed cones, and serotiny sometimes is like broken by just sunlight or by long-term drying out. But in lodgepole pine, there's a significant portion of cones that are really like their construction is such that they need to be fire cued, and so they need that additional heat from the fire to melt off the resinous seal that kind of keeps them closed up, and then over time they can dry and open up, and then they drop their seeds into that finished seed bed or that prepared seed bed. This is also a characteristic in knobcone pine. We find it in giant sequoia. So that's, it's not just a lodgepole pine thing that has serotinous cones. Another way that plants can respond to fire is to have seeds themselves that maybe accumulate in the soil seed bank, but they need a signal in order to know that they have the right above ground conditions. And their signal is fire. And so there's two ways that I know of that this can happen. One is just the heat, right? So temperature induced germination. So it's a scarification process. So seeds need some form of scarification to break up the seed coat, allow moisture and oxygen to get in, to allow the embryo to actually start to form and to break out of dormancy, right? So in these temperature-induced germination species, it's the temperature itself that scarifies the seeds and cracks them and then allows moisture and oxygen to get in and break dormancy in that, right? So really common in some of our ceanothus species. So think of Ceanothus velutinus, snowbrush, really a common species in that, but also in our in like our well, you'll see it in the Arctostaphylos species, so barberry and manzanita. So those are the other species that I can think of, and there's probably more, right? And then there's a few species that actually respond to chemical signals that are associated with smoke and other byproducts of the burning. And so these smoke-induced germination plants, the one I could look up and think of here is the scarlet bugler. That's more of a Northern California plant. But there's smoke-induced germination of seeds in some of these particular species. So that can be an important factor there in allowing that plant to be well adapted to post-fire regeneration and to really come in and repopulate those sites. Another thing, and I mentioned the Mariposa lily early on. So one of the kind of really classic examples of fire stimulated flowering is lily families. Lots of lilies are fire stimulated. I gave that example of Mariposa lily. Here's another one from South Africa, the fire lily. It just really profusely makes its flowers following fire. Now, a lot of the literature around these fire flowering plants. We call them that, but the reality is we can often get them to flower if we do other forms of relatively intense disturbance to the surface. So it's not 100% clear in all cases that they are really fire stimulated. Maybe it's just that that they have open ground. So we're not 100% sure in all those cases, but certainly fire provides that impetus in many cases because it's creating that conditions that allow the plants to effectively bloom. Now, another way that plants can be adapted to fire is to be damaged by the fire or even killed by the fire pretty readily, but to have light seed that can carry a long ways on the wind, which allows them to really rapidly repopulate or colonize places that have been opened up or disturbed by fire. So fireweed is a really common example of that. You might think many of your thistle species as things that really respond to those open areas. And it's not so much that they're resistant to fire, but they are resilient to fire because if there's any of them left in refugia within range of the area, that those seeds can distribute a long ways really rapidly, and you get really rapid recolonization of the site from these wind dispersed species. Another adaptation, long list of these. We're coming close to the end here with this list of adaptations. There are some plants that really specifically kind of have designed, if you will, stages of growth that have different interactions with fire. Okay. So longleaf pine is a good example of this. That's a southeastern United States species. And it actually exists when it first starts growing from seed. It has a grass stage. It looks like bunch grass, doesn't it? That looks darn like bunch grass. But that's actually the early stage of development of longleaf pine. And in this stage, it can get burnt over repeatedly. And because it still hasn't moved its meristem up very high, um, it gets burned over. And like bunch grass, it just kind of reproduces those leaves. And then it burns over again, it reproduces those leaves. And all the time that root system is expanding and that little stem there is getting bigger in diameter. And when it hits about an inch in diameter, all of a sudden they just start to pop up and they really rapidly grow. So now that adaptation is that now if fire goes through, there's more distance between the associated vegetation and this young tree. It's pushing it's going to have its meristem here now at this end, and it's going to move up really rapidly. So they can grow, really really fast once they hit that 1 inch in stem diameter. And then that gets them rapidly up to where they can outcompete the surrounding vegetation and be away from the impacts of fire. So really kind of a cool example of how plants can be adapted to an ecosystem. And then another way, and I think this is my last in this series, is to think of plants sometimes as kind of specifically doing things that kill off their neighbors, or maybe even kill off their own children, as horrible as that sounds, right? So ponderosa pine does both. So here's ponderosa pine that's had pretty frequent fire through it. And you can see that it's been a little while since it's had fire. So it's had several years to, get a good batch of natural regeneration going here. It's grown up a little bit here. It's not so high that it's going to be problematic yet. But if it gets much bigger, it's gonna reach the stage where it could be a ladder fuel and be problematic. And so with frequent fire going through here, because the ponderosa pine drops so many needles, there's going to be a fairly significant surface level fire that can burn through here, and it's probably going to kill most or all of these little seedlings. So with the frequent fire regime that ponderosa pine had historically, there would not have been very much accumulation of seedlings under existing ponderosa pine, wherever they could drop their needles. There just would have been too much fuel mass there and it would have knocked those out. But if one of these guys dies and then quits making that needle mass, then that becomes an area where the new ponderosa pine can get established. So really good mechanism for allowing these things to exist across the landscape. Now, if the shrubs start to grow in and like get missed for too many fire intervals and start to get a little bit big, they accumulate lots of those fallen needles. We call it needle drape. It adds a lot of fire receptive biomass to the shrubs. Now, if fire comes through, there's a much higher likelihood that we're going to have intense fire here that's going to kill off this shrub. In this case, this is bitterbrush, right? And that's going to reduce the competition for the adjacent ponderosa pine. So it's a kill your neighbor kind of adaptation to allow that ponderosa pine to maintain its growth space and to really maintain an area where the potential for reproduction of its own species is going to be greater once that spot opens up. Instead of having it occupied by brush, it's going to be occupied, it's going to be more open and have that better receptivity to the ponderosa pine growing up in that area once it opens up. So kind of a cool adaptation. So again, we might summarize these by kind of lumping them into some categories here, right? So this was a relatively old paper, but I think it's still really useful to think of here that you can take most of these plant adaptations that are related to fire and put them into 5 categories. So you've got things that are resistors, like those thick bark species, like the species that have really like tall stems with few branches down low, things that like allow them to experience fire and just really not be much impacted by it, right? You've got the endurers. Those are the ones that like maybe the above ground biomass part gets killed off, but they endure that. They find a way to come back. So those are your resprouters. So the below ground portion stays alive and we can resprout and we can rebuild that, right? So those endurers are those resprouters. Then you've got evaders. So these are ways that you could get around the impact of the fire. The fire comes there, but you found a way to get around it. And so serotinous cones, that's your canopy seed bank, or those soil seed banks that are fire activated or smoke activated, right? That can be a way that you can evade the impact of fire, even though you've been exposed to it and been impacted by it, right? Then you've got invaders. So those are the colonizers that can go long distances, light seeds that float on the air well. And so they can be the ones that really repopulate those areas, right? And that's a form of fire adaptation. There's a lot of plants that we consider to be fire ephemeral. And so they can be there for a relatively short time until the next fire comes through, but then they rapidly repopulate from adjacent areas. And then finally, there are the avoiders, and the literature around fire uses avoider in different ways, but this is using it kind of in the classical definition of avoiding the fire by being those species that really they're sensitive to fire. So the places where they thrive and survive are the places that don't get the fire. So they're in the refugia, they're in the drainage that maintains the higher moisture content. They're in the areas around the spring. They're on the north facing slopes that tend to have the more moist conditions. And so the avoiders are going to populate those areas. And then that may mean that they can spread over time into areas that have fire, but they always have to have that refuge because that's the place where they, as a population, retreat back to when the fire comes through. All right. So let me take a quick look again at Q&A. McKenna, what paper is the bark thickness graph from? I will find that and post it. I've got the citation for it. It's just not one of the things that I posted, but I'll find it and post it. And would Western juniper be an avoider? Hadn't thought about Western juniper being an avoider. But so Western juniper, to an extent, is an avoider because the places where it would likely survive in like a frequent fire regime would be the rocky outcroppings in places that maybe don't get as much fire. But my observation of Western juniper is that it actually kind of produces its own defensible space in many cases. So if you look at junipers, once they've like achieved any significant size, so even like maybe 8 or 10 inches in stem diameter down relatively low, they start to lift their lower branches a little bit and they produce a relatively deep mulch bed from their fine foliage. It's really densely compacted. And so when fire comes up to that shaded area often holds a little moisture or just doesn't burn well, or if it does, it's like a slower smoldering combustion. The trees seem to be pretty resilient to that. It doesn't get any flames that can leap up into it. And so they tend to be, I would almost say in some cases, resistors because they have found a mechanism to keep fire from getting into them. So maybe they're avoiders, but I think they're almost resistors in some cases because they just don't have the fire that really has enough intensity when it reaches them in order to be able to catch them on fire. So you could probably put them in either category there, depending on how you think about that. But they're pretty interesting in the way that they are adapted to fire. How do you adjust? So this is Pam's question. How do you adjust fire frequency expectations due to the effects of climate change? I think that probably Micah's going to spend quite a bit of time thinking about that when he talks more about fire regimes. So let me put that one on the back burner, and that can be one that if we don't quite get that figured out in Micah's talk, we can come back to that, and I can talk a little bit more when I have my next presentation when I'm talking about dry side plants there. So I'm gonna close it off at that and ask my folks here to make sure that I'm true to the things that I'll look up because they've gone away now from the list. And so make sure that I am answering those questions and adding that extra information into our website. All right, so let's forge ahead here. So to date, or to this point, I've been really like focused on impacts of fire on plant communities. And I'm not a wildlife biologist, but I just want to acknowledge here that the interactions and those kind of adaptive traits that we've been talking about aren't limited to plants. So the fauna that interacts with the flora can have similar kinds of traits that allow it to either be resistant or avoiding or resilient to as a population. So there's lots of ways that animals can interact with the plant communities and the fire and have different levels of resistance and resilience and so on, right? So maybe it means that the lizards know that there's subterranean places that they can go to get away with that, or maybe they're going to flee out into places that are more protected or find damper areas. Maybe, insects are, part of that population is going to be killed, but part of it also going to be attracted and repopulate. Maybe the heat's going to move some away, but there's lots of insects that are attracted to, the aerosols and things that are produced by the burning process, and they come in and are really attracted to those recently scorched and charred trees. Maybe it means that species are going to move out of areas, but then come back in following, and it's probably going to be a different subset of creatures that are going to be in those areas and taking advantage of that now changed habitat, right? So woodpeckers that are very adapted to recently charred trees, owls that come in and make use of very specific habitat, rodents that come in and make use of specific habitat, and so on. So lots of specific interactions there that are in many cases a secondary fire effect impacting those animal species. Now, I just want to kind of tie some of these pieces together and put it over a little bit more like a recurring time frame. So with fire, we got to think about fire as driving both disturbance and adaptation. That's, again, not a one-time thing, but it's something that's ongoing. It works in iterations, and it has the potential to be cumulative. So sometimes it adds up and then cycles. Sometimes it cycles more frequently, but just depending on what particular ecosystem we're working in and what its fire regime in, there's going to be some different pathways. So these graphs, hopefully you can see these. They're kind of small, but we're just looking at these different colored dots in here, right? And you're going to envision that these different colored dots are different species within an ecosystem, right? So we could have a system where we've got some relative, stable distribution of 3 different species, but then we have fire, and some of these species, or in this case, one of these species, is better fit to survive or repopulate the fire, the post-fire environment than the others. And that's going to mean that the result of that, at least from that event, is that we're going to favor increasing the proportion of the population of that fire fit species and decreasing the proportion of the other less fire fit species. Makes sense, doesn't it? Right? Here's another way that we can look at these potential interactions. So now in this particular example, we've just got 2 species. And again, we have the relative balance of these two species over time. We have a fire. One of them is not very resilient to fire. One of them is more resilient or resistant to fire. And so that's going to drive that change in species composition between across time, right? So the fire drove that species composition, right? But over time now, we can see multiple fires over time, and we can see the recovery over time. And over time, we start to get, the other species coming back. And that longer term, the longer we go with fire exclusion, now we've got here a species that is more fit, more attuned or adapted to fire exclusion. So it starts to kind of take over while the fire adapted species, not getting its fire, gets outcompeted, right? And so now we've reverted back to this condition where we've got more of the species that is adapted to having little fire and less of the species that's adapted to having fire. And so like we had the question about how are fire regimes changing and adapt in face of climate change. This is one of the things that we're likely to see is that we'll have some places that will have increased fire frequency and increased fire intensity, increased fire severity. We're going to drive species composition to those species that are more able to resist that, or at least more able to respond to it. So it might drive it to, like, we're going to have in some places fewer forests, but more annual grasses that can really readily respond to that frequent fire interval, right? This is the case that we've been experiencing for a long time because we as humans have excluded fire from many of Earth's landscapes for a long time, very purposefully, very successfully. And so we have driven the composition of those ecosystems towards things that are more adapted to going without fire. But that also means that in many cases, we've built up the overall biomass. And now when fire does occur, now we have higher potential of having a more intense and more severe fire, right? Here's a final example of the ways that this could kind of come about. So now we've got a mix here of three species accumulated over time. We have a fire. The fire in this case has both the impacts of, some species are better fit to the fire than others, but the fire only hit part of the landscape. And so now, in this particular case, we've got fire that occurred here. It's fit to fire. And so we've had this particular area now become much more populated by this fire fit species. We've got another area over here that didn't get the fire and it regenerates within that, right? And so depending on this arrangement across the landscape, we could end up with very distinct mosaic of some areas in one species and some areas in another species. And then I would just note here that here's this one little dot in here representing the species that does not have high fitness to fire, right? And I would say that this is kind of the example that we would experience in many of our east side Oregon forests, where we've had now long-term fire suppression. So instead of having this condition where we had maybe some western larch and some ponderosa pine with some Doug fir scattered down, we get a buildup over time. If we don't have the fire, we get more and more of these species composition like the white fir or grand fir, which are not resilient to fire, except that they're the avoiders. They live in the refugia, right? But if you go a long time between fires, they can invade into these areas that have not had the fire. So the fire regimes are changing because the composition and density of the forest is changing because of long-term fire exclusion. So this is what it could be if we had fire, but if we lack fire, we're going to see these species kind of take over and fill in the spaces between these others. So kind of a mental exercise there. A really good resource, I've mentioned this before in other webinars, but if you're interested in doing some individual research on the effect of fire on individual flora and fauna species, go to the Fire Effects Information System. You can just Google it. You don't have to write down the whole address here, although I did post it from our website. The Fire Effects Information System is a great resource where lots of publications get archived and kind of cross-referenced, so you can find lots of good information. And they The people who maintain that often will pull together various synthesis articles so they can kind of look at the overall implications of all this different research on different species. Okay, we're wrapping up, getting close here. So I want to just make the case that fire is really complex in our Earth environments. So we can't think of fire as being something that just impacts plants and animals that are on the land. We have to think of fire as something that has broad scale effects in all of our major systems. So our atmosphere, the air, our hydrosphere, the water, the biosphere, obviously, but also the geosphere. So atmospherically, fire um, it puts carbon dioxide back in air, but it resets various plant processes that are going to recapture that process. So there's a recycling of that. It's going to release other particulate matters that can have impacts on rainfall, that can change global temperatures through changing the albedo of the earth. It can have impacts on our hydrosphere through changing rates of snow melt. It can change water chemistry through the chemicals that run off following fires. So very much an interaction there. It can change landforms by changing the plant matter on those landforms or directly through the heating and raveling of the soil material and the rock material. And obviously it has huge impacts in the biosphere with these long-term adaptations of plants responding to fire. So impacts all of those. And there's a really complex diagram there that just says all of these things are interrelated. They all play together. And changes in climate impact fire, changes in land cover impact fire, fire income impacts changes in land cover, fire impacts soil, soil impacts vegetation, which is fuel for the fire. So they all fit together, right? So I think that's kind of obvious to those of us who really spend time thinking about fire, but I kind of want to drive that home. So I'm going to close with this, just next few slides here. Do me a favor and jump into chat again. And I want you to tell me what you think are the three primary ignition sources for fire occurring on planet Earth. Three primary ignition sources. So just write three ignition sources in. What do you think they are, right? So let's see what people are doing. So in the chat box, so I'm seeing lightning, humans, volcanoes, people, humans, lightning, humans, lightning. Okay, yep. Good. Human, volcanism, lightning. Okay. All right. Good. Okay. So lots of good stuff. So statistically, the primary sources are lightning, volcanoes, and people. So most of you said that, right? Now, others, so some of you gave other ways that we can conceivably have ignitions, and it does occasionally happen that we'll have, decomposition that will start fire. But for the most part, these are the three big ones, right? So volcanoes, obviously, really high temperatures. So when you have those, anything that comes in contact with it is going to be burned. A lot of lightning strikes across our planet, and it's not uniform. Places like part of the reason that the East Coast of the United States and Florida in particular gets lots of fires, they have lots of potential ignition. So there's just lots of that stuff going on. Volcanoes are more common along our region, but obviously those are more rare events. But people historically and prehistorically have really been carriers and users of fire. If you think of beavers as dam builders, humans are fire builders. So humans have modified environments for pretty much as long as we've been humans by using fire. So we use that to change landscapes, to change vegetation composition, to change the habitat for animals. So many different ways, right? So these are the big three. So it's like pretty logical for us to think of lightning strikes as being historically a source of fire. volcanoes, maybe we don't think that as much, but it's logical once you think about it. But I want to focus a little bit on this human interaction because this is really essential to understanding fires in this kind of bigger context, right? So if we think about fire-dominated U.S. history, right? Um, a lot of the places where we see frequent fire, that was not just because they had frequent lightning or lots of volcanoes. It was because humans there used fire to manage those landscapes. So indigenous people in the United States used fire extensively. And many of the places where we see the shortest fire return intervals, those really frequent fire return intervals, were because people were burning areas frequently. If you burn off the grassy material around your community on a regular basis, the potential that your community is going to be burned up by a fire started by someone else or by lightning or by a volcano becomes lessened. There's not fuel there to burn that off. If you burn off the areas where you want to collect material to make your baskets, you can rely on the resprouting capacity of those shrubs in order to have things material that's more suitable to those baskets. If you use the Western landscape and you think of burning, maybe we're doing this to provide, grazing range for our horses. Maybe we're doing this to provide, in some cases, smoke that cools streams to promote spawning runs for anadromous fish, right? So there's all kinds of different ways that native peoples were using fire as a really active tool to manage their landscape, both to provide themselves with protected spaces, to protect them from other forms of fire, to protect them from other peoples, to provide better hunting, to provide better food sources. It was just like ubiquitous. And this is true way back in history. I mean, we find active fire use by humans way back in the archaeological record, way back into prehistory. So humans, as I said, we are fire creatures and we've been engaged with fire for long periods of time. The thing that has really impacted our fire regimes in many of our settled landscapes, that's probably not the right word, many of our Western settled landscapes or Western occupied landscapes has been this last 150, 200 years in many cases of pretty extensive fire suppression, fire exclusion, that now instead of having frequent low intensity fires, now we're having less frequent high intensity fires that have the potential for higher severity. Micah will go way more into detail when he talks about fire regimes, I'm sure of that, so I don't want to steal his thunder there. Okay. So we as people nowadays, we really face a conundrum because not only have we modified our landscapes to have less frequent fire, we've forced it into that condition. In doing so, we've modified the plant communities in those landscapes. So we have changed the potential for fire from being something that maybe was, high potential for relatively frequent but low intensity and low severity fire. And now we have a much higher potential that we're going to get a high severity fire, a crown fire, something that spreads rapidly across the landscape. And we've changed the frequency distribution of the sizes of fire from more smaller fires to fewer larger fires. And so that's another big factor that we've had. And to top it off, we have built into this fire interface, right? So we build our homes in places where it's beautiful, but these are still landscapes very susceptible to fire. And eventually fire will come. And now, instead of being a landscape where fire can burn across and have a nice mosaic of impacts, of severities, and will recover because of adjacent refuge and so on, and the animals will move and then come back, right? Now we say, well, we need to protect all of these homes from this fire. We need to protect this power line from this fire. We need to protect our road infrastructure from these fires, right? And that's probably long term. I'm not even going to say probably. That is not long term sustainable. We have to think about how we can exist in landscapes that are ecologically adapted to fire and do so in a manner where fire can exist peaceably with us. And so the challenge for us as humans is to think beyond putting fires out and think about how we exist in that fire adapted ecosystem. So I will kind of close with this side, or close to close with this slide, that's saying a lot of folks are now thinking that we need to like relabel fire and think of this as pyrogeography. So geography is us as humans thinking about the lay of the land, and we need to put fire back into that. And we need to treat it as not just an ecological process, not just as a biochemical process, but as a social process, as a cultural process, where fire really lies at this intersection of biology, the intersection of geology and geophysical environments, and our society and culture, right? So here I really will close, right? So last kind of statements here just to tie this down. So let's do this. Fire is absolutely essential to our understanding of the evolution and distribution of life on Earth. And that is true at every temporal and spatial scale. Okay. So just like I think that's a really true statement. And just kind of ponder that a bit, right? I put the paper that this came from. This is a really recent paper by a whole bunch of really high-powered fire ecologists and fire scientists, right? It's on our website. It's Kobziar Principles of Fire Ecology. Awesome, right? So principle 2, fire is an integrator. It takes the biotic or living and the non-living, the above ground and the below ground, and the way that it works, it involves all of them. So it's not just about what it's above ground, it's all of those pieces together, right? Fire is not a one-time thing. It has all of these dynamic feedback loops, right? And in the process, it organizes ecosystems. It defines or influences their structure, their composition, and hence their function. So all those pieces come together. Fire is absolutely essential to that. And it may mean that particular ecosystem is organized by frequent fire. It may mean it's organized by infrequent fire, right? But it's there nonetheless, right? Um, these drivers of these feedbacks is the fire behavior that we talked about. So fire behavior and fire effects drive the statement here says a continuum of process elements, right? And some are deterministic, meaning we can really we can predict them. We know what they're going to be, right? Some are stochastic, meaning there's a whole lot of randomness to it, right? And so we've got this combination of predictable and unpredictable. And if you spend any time studying fire, there's stuff that's predictable, and then every time there's something about it that doesn't go the way you thought it was, right? And so it's both predictable and unpredictable. And again, that's true across all spatial scales and time scales. And then finally, we as humans, we impact fire. We impact contemporary fire through the processes that we undertake, through our thought process for what fire is and how we should engage with it, through our focus on putting fires out. And I'm not saying that's bad. I spend my summers fighting fires, right? But we also have to recognize that people, humans, have a really long history with fire, and that we have used fire to the extent that our behavior in ecosystems has modified those ecosystems. And it's done so over really long time scales. And how we move forward with fire is going to an extent, drive our future. It's going to how we impact with climate, how we impact with land use, how we impact with our social perceptions of fire. All those are going to drive the future. So there's the foundation, a lot of stuff. Please refer back to the website. If you want to see the recording of this, we'll get it posted pretty soon. I'm going to remind you that the next one in this series is not next week, but the week after. Micah's going to talk to you about fire regimes. He's really good with that stuff. I know he'll do a great job with that and build on the stuff that I've covered here. So thanks for sticking with me for a couple minutes past our normal stopping time. And if you want to leave, no problem. But I think there's a couple more questions here in Q&A. And I will, Michelle is asking, is OSU developing a pyrogeography program? Please say yes. Not well, so I would say that Meg Krawchuk, when she teaches her fire ecology class, she often refers to it as pyrogeography. She thinks of it that way. So there is a component of that. I'm currently teaching that class for her while she's off doing some other cool stuff. And we're really digging it deep into the concepts around fire ecology and this whole human dynamic interaction with it. And while we have lots of forestry and natural resources students in there, I would say about a quarter of our students are actually out of the geography department. And so 81 students in that class this term with a ton of really interesting stuff going on with people asking great questions. So not 100% that we're developing pyrogeography, but certainly it's like within the scope of work that we're doing at OSU. So thanks everybody. And if my really great helpers here can help me for just a minute, I want to make sure that I capture any of the elements of things that I said I would follow up in and make sure I get stuff posted back to the website to answer those more challenging questions. Thanks, everybody.
It looks like Jake just put the keyword in the chat, which is
Yep.
what, Jake?
Yeah, real quick, the SAF keyword for tonight is ecology.
Cool. Thank you. And thank you to my helpers. Oh, so Avery, you can get proof of attendance for CEUs by if you need SAF, you get the form off the website and you fill that out and you use the keyword ecology. If it's CEUs for Associated Oregon Loggers or for Certified Burn Manager, you make sure that you connect with Jake Putney. His information is on the website, and he can get you that information that says that you did that. If it's International Society of Arboriculture, ISA. Again, contact Jake. He can give you that note. If you need it for something else, talk to Jake. Jake is he has long served as our coordinator of our CEUs, does a great job with that.
Yep, thanks, John. Yeah, just send me an email and I can help you get those credits.
That was much more concise.
Jake, do you want to throw your email in the chat?
Yeah.
John, I have an email ready to send off to you with all the questions you said you would respond to.
You are awesome. Thank you.
Yep.
Okay. All right.
Nicely done.
I'm going to sign off then, and I just thank everybody for your participation tonight, and I hope we'll see you on the next one.